In this video, we're going to review VSEPR theory. So previously we reviewed hybridization, and hybridization was a bonding theory. It helped us explain the types of atomic orbitals that form when chemical bonds formed. But VSEPR theory is a bit of a simpler theory, and it's more effective at predicting the shapes of molecules and bond angles. So VSEPR, V-S-E-P-R, is short for valence shell electron pair repulsion. And so effectively this theory is used to describe specifically shapes of molecules and bond angles. It doesn't really discuss the types of atomic orbitals that are formed, such as D2sp3 or dsp3 or sp2. It's mostly just looking at the shapes and the bond angles. So here are a few key principles that we need to follow. We're always going to begin with the Lewis structure of the compound because the valence shell of the central atom determines the shape of the molecule. And this is the most important aspect of the theory. And put little stars right here, which is that the shape of the molecule is determined by creating the maximum distance apart between pairs of electrons, both bonded and lone pairs. And that is, electron pairs are arranged to minimize repulsions. So bonds and lone pairs mutually repel each other because they're made of electrons, and electrons are negatively charged, and things that have the same charge repel each other. So we create shapes that minimize those repulsions. In VSEPR, we have double and triple bonds counting geometrically the same as single bonds. And then there's some other facts here that are important to note as well, but we'll use those as they come up in the theory. So we're going to start off right here with linear electron geometry. Okay, so the first molecule that we're going to encounter is BeH2. And so I'll just go ahead and draw these Lewis structures. Unless there's a Lewis structure that I think it's worth going over how to draw, I'm just going to provide these in the video. So the bond pairs, we look at these right here. There's two bond pairs. And when we talk about lone pairs, what we mean by lone pairs on the central atom. So look at my central atom, there's 0 lone pairs, total pairs of 2, and the general formula is A for your central atom and 2 surrounding atoms. So when I think about this, how would I arrange my surrounding atoms to minimize the repulsions of the electrons? Well, by putting them this way right here, these electron pairs are maximally spaced apart to minimize repulsions. Okay? This electronic geometry is called linear. And since there are no lone pairs on the central atom, the molecular geometry will be the same, and we'll end up with a bond angle of 180 degrees. Okay, and that molecular geometry again is also linear. Okay, so that deals with molecules that have linear electron geometry. Now we're going to move on, and we're going to deal with molecules that have trigonal planar electron geometry. First molecule that we're going to look at is BH3. The Lewis structure for BH3 looks like this. Now again, this is just the Lewis structure. This doesn't really give us a sense of the actual shape of the molecule. When we talk about bond pairs, we're looking around the central atom. There's 1, 2, 3 bond pairs. No lone pairs on the central atom. Total of 3 pairs. And a general formula is AX3. Well, if I think about my central atom being in the middle and my surrounding atoms, how would I position these surrounding atoms to minimize the repulsions? Well, that would be in a triangular plane like this. Right? And again, as you can see, this is trigonal planar electron geometry. Molecular geometry would be B, H like this, all within a plane, no 3D structures required, and if they're evenly spaced out, the bond angle there is 120 degrees, and this is called trigonal planar. Okay, now what we're going to do is we are going to look at the NO2 negative ion. So this is the nitrite ion. For the nitrite ion, I'm actually going to go through the process of showing how to do this Lewis structure. And for that, I'm going to cut and paste a set of instructions that we acquired back when we were doing hybridization. Okay, so these are the instructions that you can find in the hybridization section of your note. It says decide which atoms are the central atom and count all the valence electrons. So I'm going to put nitrogen in the middle as my central atom, and then I'm going to put oxygen around it. And then I'm going to count up my valence electrons. So nitrogen has 5 valence electrons, and oxygen has 6 valence electrons, and then I'm going to multiply that by 2. I notice that there's a negative charge, so I've got an extra electron. This is a total of 18 electrons to place. Now it says in step 2, bond all atoms to the central atom. So I'm going to bond, and I'm going to bond. That takes care of 4 electrons. That'll put me at 14 electrons. So I've got 14 electrons left to place. Step 3, complete the octets of the surrounding atom. An octet means that it has 8 electrons around it, oct being the prefix for 8. So I look at my surrounding atoms like oxygen, and I'm going to complete these octets. Okay, so 2, 4, 6, 8. Yep. 2, 4, 6, and then with the bond pair, that's 8. So I placed about 12 of these electrons. So now I have 2 electrons left over. Place any remaining electron pairs on the central atom. Okay, so electron pairs are going on the central atom, and now I have 0 electrons left to place. So I'm going to get rid of all this. This is getting a bit messy. Okay, so I've got 0 electrons left to place. And it says, if the central atom does not have an octet, take electron pairs from surrounding atoms and make double or triple bonds. So what I see right here is I see that nitrogen has 2, 4, 6 electrons, whereas the oxygens all have 8. So I need nitrogen to gain another 2 electrons, so I'm going to just take them. It doesn't matter where I take them from. And I'm going to make a double bond here. So I took those 2 electrons, and now I'm making a double bond with oxygen. And now nitrogen has its octet. Oxygens have their octet. I do a square bracket and charge for the nitrite ion. The other thing that I want to highlight right here is something that we learned previously when we were talking about VSEPR theory. Okay, we can see right here it says, in this theory, double and triple bonds can be viewed geometrically the same as single bonds. Okay, so cutting back to this molecule, what I'll just put is a little note to myself, and I'll say I'm going to count this as a single bond. Count this as a single bond right there. Okay. So when I look at the number of bond pairs around my nitrogen, I count this as 1, and then that's 2. Now I have a lone pair on the central atom. Still a total of 3, and that's because the electron geometry I'm dealing with right here is the title of this section, trigonal planar electron geometry, so I should have 3 electron pairs around it. And now I'll say AX2E, where E is my lone pair. Okay, so when I have a lone pair, essentially I have my surrounding atoms, but then I have this right here at the top. This is my lone pair. And what that lone pair does is that it strongly repels these bonded pairs of electrons down and pushes these closer together. This is still trigonal planar. I'm just going to put trigonal planar right here. Okay, not sure that that was necessarily a big reduction in writing, but whatever. Okay, so now I go nitrogen, oxygen, okay, and my double bond for my oxygen there. That's based on my Lewis structure that I had right there. Okay. So recalling that these electrons are being pushing down on these bonding pairs, that means that this bond angle is actually going to be less than 120 degrees typically. But because there's a double bond, the double bond is bulky and takes up more space. Now you might recall that double bonds have pi electrons that exist above and below the bond axis, so they push out further. So instead of writing less than 120 because this is being pushed down, the double bonds push back up, and we get approximately 120 degrees. Now the shape of this molecule is not going to be trigonal planar, even though that's the electron geometry that it is based on. It's actually called a V-shaped or bent molecule. The next three molecules we are going to take a look at are based on tetrahedral electron geometry. So tetrahedral electron geometry exists when you have 4 electron pairs around a central atom. So this is the Lewis structure for the ammonium ion, and we arrive at this by saying, okay, well, nitrogen has 5 electrons, hydrogen has 1 electron times 4, so I should have 9, but then I'm going to subtract 1 electron because it's got a positive charge. So I have 8 electrons to place, you place them, and you end up with this structure. Bond pairs is 4, lone pairs is 0, total pairs is 4, and we get AX4. The electron geometry for tetrahedral is as follows. You have a central atom, you have an X coming forward, an X coming down, an X coming all the way forward right there, and an X in the back. All right, and this is tetrahedral. The surrounding atoms are placed in this manner to minimize the repulsions between the electron pairs. If we look at it like this, this would suggest that everything is at a 90 degree, but when they are spaced this way, and I'll draw it out over here, when I have my bond pairs spaced out in this manner, I can actually get a slightly better spacing. I can get 109.5 degrees, and all of them have that right there. And again, that is going to be tetrahedral. Okay, and so that's the bond angle in a tetrahedral molecule is 109.5. Moving on to ammonia. Ammonia looks as follows. We've got this right here. Okay, 3 pairs of bonding pairs, 1 lone pair on the central atom for a total of 4. This is AX3E. And so now what I have is, again, I still have tetrahedral electron geometry. But now I have this lone pair that exists at the top. So again, this is still tetrahedral. Okay. And so with my ammonia that has this lone pair at the top, I've got the hydrogen coming down like this and like this. And as you can see, or maybe you can see, it might be hard to see, but basically you've got basically like a triangular plane on the bottom here, and then it comes up to a peak. So if we trace this out, I think you can see that that makes a triangular pyramid. Okay, I'm just going to undo that writing so you can see that, but that's called trigonal pyramidal. What happens here is that this lone pair pushes down on all 3 of those bonds and it squeezes them close together. So this is no longer 109.5. All we need to say is that it's less than 109.5. Technically, for the ammonia molecule, the bond angle is 107.9 degrees for the ammonia molecule. You don't need to know that, but it's one of those facts that's helpful to know. Okay, quickly drawing the water Lewis structure. We don't need to go through the process for that. We know how to do this. Okay, 2 bond pairs, 2 lone pairs, 4 pairs total, AX2E2, and we end up with this. Okay, still tetrahedral, okay, but now we've got a lone pair on the top, and we've got a lone pair going behind. It doesn't really matter where you draw them. Now, these lone pairs are strongly repelling each other. They are also then further repelling these bond pairs. And then these bond pairs weakly repel each other as well. Okay? But the strongest repulsions are happening between these lone pairs and lone pairs. All right? Again, since there are 4 electron pairs around here, this is still tetrahedral geometry, electron geometry. All of these, as you can see by the bonded title of this section, are tetrahedral electron geometry. Now, we have all of this can now sit in one plane. This is V-shaped. Okay, V-shaped or bent. And in this case right here, we have to be careful. It's not the same V-shaped or bend that we saw up here where it was, less than 120 or approximately 120. Here, it's going to be less than 109.5 because it's based on the electron geometry of tetrahedral. Okay. Again, if you want to know the exact angle, it's 104.5. It's less than the ammonia angle, and that's because we have now two lone pairs really strongly repelling and then further repelling those bond pairs, so it's pushing them even closer. Okay, so that covers the first sets of families that we wanted to take a look at: linear electron geometry, trigonal planar electron geometry, and tetrahedral electron geometry. And in the next video, we'll take a look at the electron geometry that's based on trigonal bipyramidal.